So if not, I will try to continue. So we had to start to talk about morphisms. So we had introduced regular and rational functions. Subset of the rational functions on our variety, which is x is, say, a fine projective. Open. And maybe not go again through the definition of these regular functions, but a regular function defines indeed a function from u to k. And then I had defined the morphism. So x and y are varieties. A morphism phi from x to y is a map from x to y which is first continuous. So the inverse image of every open subset of y is an open subset of x, and it's compatible with regular functions. So for every u subset y open, well, I could say that, and every f, regular function on u, we have that that if I take f, which was just defined as the composition f composed with phi, is a regular function on the inverse open subset in X, because phi is continuous. This was the definition, and we had seen obviously the composition of morphism is a morphism, and to be a morphism is a local property. So if a map is a morphism in the neighborhood of every point on the source, then it is a morphism. So now we want to see that we also can find a more concrete way of describing morphisms coordinate-wise. First, we do this in the affine case. So a morphism from any variety to a subvariety of a affine space is just a map which is coordinate-wise given by regular functions. So that x and y be varieties with y contained in AN, a map from x to y is a morphism if and only if there exist regular functions f1 to fn, as many as their coordinates on an, which are regular on the whole of X such that if I take the image point of P, just its coordinates are just the values of these regular functions at P for all P. So just each coordinate of the map is a regular function. That's equivalent to being a morphism. So we write F1 to Fn. So this somewhat more abstract definition is equivalent, if the target lies in defined space, to this more concrete one. So there are two directions. Let me try to show it. One direction, which actually looks like it might be the more difficult one, namely that a morphism is given in this way, is almost trivial. So let y1 to yn be the coordinate functions on an. So on y. So that means the restriction of the coordinates on y, which are regular functions. So then we put fi, for I equal 1 to n, to be the pullback of yi. So this, I want to prove this direction. I assume that phi is a morphism. So as phi is a morphism, we find that, as a pullback of a regular function, so the fi are regular functions. Then, as phi is a morphism, we have that fi the regular function on the inverse image of y, but the inverse image of y is the whole of x. And obviously, if I have a point P, x, we have a phi of P. The coordinates of phi of P are just the coordinate functions applied to phi of P. So 1 n of phi of P. But this composition is just the fi. So this is quite obvious. So if phi is a morphism and the target lies in a defined space, then the coordinates are given by regular functions, by functions which are regular on the whole of x. Now, that's, and if you remember, this was also, we used a similar argument before when we were looking at polynomial maps. And, okay, so now we want to look at the other direction. So we just define phi equal to f1 to fn with fe of x, and we assume also, so maybe I write y with fe regular functions on x. So we can assume we are given a map from x to y, which coordinate-wise is given by regular functions. Prior here that the map actually goes to y, not just to n, but the coordinates are supposed to be regular functions as assumed here. Then we have to show it's a morphism, so we have to show it's continuous and that the pullback of any regular function on an open subset is regular. So to show it's continuous, I want to show that the inverse of any closed subset of y is closed in X. So let subset y be closed. So then that means it's an intersection of a closed subset of an with y. So thus we can write, A is y intersected the zero set of some polynomials g1 to L, where the gi are some polynomials. Now, in this defined space. Here, maybe I could also call them yi. So, say xi are the coordinates and yi are the restrictions of them. Well, maybe I write yi to make it. Yeah? Okay. So then, what's the inverse image? So we have to, the inverse image of this is the zero set of what we get if we compose the gi with phi. And composing the gi with phi means to replace the yi in these polynomials by the fi. So this is equal to, I just write it as the zero set of g1 of f1 to fn until gl of f1 to fl. So zero set means here just the set of zeros. I mean, I had, and now you notice, so this is the gi are polynomials. We put these regular functions fi into it. So we know that regular functions are a K-algebra. So these are actually regular functions. So we have I of f1 to fn are regular functions on the whole of X. And we have seen that regular functions are continuous. So that means the zero set of a regular function is closed. Here we just have the intersection of finitely many such closed subsets. So thus, to the minus 1 of A equal to the intersection I equals 1 to L of the zero set of gi of f1 to fn is closed in X. So this means this map is continuous. And now, so now we have to see that the pullback of a regular function on an open subset is regular. This is also not particularly difficult. So let U subset Y be open and F be regular on U. So to be regular, it's enough to be regular in the neighborhood of every point. So we take a point U, then there is a neighborhood of P U. No, say neighborhood of P of P of P in Y or in U, whatever. You can write F divided by H for G and H polynomials. I mean, restrictions of polynomials to Y. One to yn, and we can assume that H has no zeros on V. So then, on phi to the minus 1 of V, we have that star of F is again G of F1 to Fn divided by H of F1 N. You know, the composition with T for polynomial is just done like that. And as in the image, so G, this is a regular function, this is a regular function. So it's a quotient of two regular functions, and the denominator does not vanish on this inverse image because the H does not vanish on the image. So with G of F1 to Fn and H of F1 Fn O of phi to the H of F1 to Fn without zero. On O of phi to the minus 1 of V. We know that if we have a regular function which has no zero on an open subset, then 1 divided by it is still a regular function, and so this quotient is a regular function. So thus F is a regular function on phi to the minus 1 of V. And now, so phi to the minus 1 of V is a neighborhood of our given point to the minus 1 of U, and we had chosen the point arbitrarily, so every point has a neighborhood on which this pullback is a regular function, so it is a regular function altogether. Okay. Okay, so this gives us this slightly more concrete way of describing morphisms, which is similar to what we had before for polynomial maps. I might mention that, I mean, just so that if just from the definition, so for, doesn't follow from this, but it's just, it follows also from this, for a variety X, a regular function say F in OX, regular on all of X, is the same as a morphism. Which I could call f from x to k. Because, or, well, a morphism x to a1. No, because it's just a morphism is a map which is coordinate-wise given by a regular function. So, therefore, these two definitions are the same. Okay. So let me look at yeah. So in the case that x and y that are both affine varieties, it follows that a morphism between them is the same as a polynomial map. So proposition that x in an, y in am affine varieties, those subsets of an and am. So a morphism from x to y is the same as a polynomial map. This is, a morphism is something which is coordinate-wise given by a regular function on the whole of x, but we know if I have an affine variety, a function which is regular on the whole of an affine variety is actually an element in AX. So this is, and so therefore it's given by a tuple of polynomial functions, and that's the definition of polynomial map. So this is because OX is AX. This is something we proved that followed from the Hilbert-Nullstellensatz. Let's just look at a few examples. Let's look again at this capital cubic, so that C be the zero set of y squared minus x to the 3 in A2. This is the capital cubic. So we had this polynomial map, which is therefore a morphism, phi, which is given, which if I call the coordinate on A1, t, this is given by t squared t to the 3 from A1 to C. So a point A in A1 is sent to A squared A, and this certainly satisfies this thing. And we had, so this is A maps to A squared third. This is, as we had seen, is a bijective morphism. We had seen it's a bijective polynomial map, and so it's a bijective morphism. And if we look at the inverse map, so, but the inverse map phi to the minus 1 was just the map from C to A1. We had already seen this, that the pair AB sent to B divided by A, if A is different from 0, and 0 if A is equal to 0. So this is not a morphism. For instance, if I take the, what is the pullback? What would be the pullback of the function t, of the coordinate function t? So if I take phi star of t, this is t composed with this map. So this is just the second coordinate function divided by the first. So this is y divided by x, which is just a rational function. And in fact, on the other hand, you can see it's regular wherever x is non-zero. So we have that. So therefore, the inverse map exists everywhere outside 0. So, so this is in Kc, but it is also in O of C without the point 0, 0. And so the inverse map is given by this thing. So thus, you could also see, therefore, that phi to the minus 1 is just the map y divided by x from C without 0, 0, 1. So this is a well-defined morphism because this is a regular function on the thing. So we see thus C without the origin isomorphic 1 without via this map. So it will be convenient in the future to slightly change our language, where I still will occasionally remind you when I do that. So I had until now said that the variety is affine when it is a closed subvariety of some affine space. Now I want to use the more standard definition, which says that the variety is called affine when it's isomorphic to a closed subvariety of affine space. So in future, call a variety affine is isomorphic to a closed subvariety, some affine space. So it's not clear that whether these are any more than we had before, but we want to show now that with this new definition, there are somewhat more affine varieties than before. In particular, we can have an strict open subvariety of an affine variety, which is still affine. We can take away some closed subsets from affine varieties and they stay affine. But obviously they are not closed subsets of the same affine space. And this is something that turns out to be useful because it means that one can use that to show that every variety has an open cover by affine varieties. So this is a following definition. Let X in AN be a closed subvariety. And we take a polynomial which does not vanish on the whole of X. Okay. So the principal open defined by f is xf, which is just x without the zero set of f. Obviously, this is an open subset of x, and not completely clear here, but okay. But it could still be that the zero set of f intersects x. No, in fact, it almost always will. And now I want to show this is always an affine variety. So that means xf is a closed subset of some affine space. Obviously, if it cannot be a closed subset of the same affine space because it's strictly smaller than x. It's an open subset of this. So, but I want to see it's a closed subset of affine space one dimension larger. And it's slightly similar to what we did when we proved the strong version of the Nullstellensatz. So we let Z to be the zero set of the ideal of x and the polynomial our f times xn plus 1, so an n plus first variable minus 1. We take the zero set of, so this is the zero set in one variable more, so in an plus 1. The first n coordinates should belong in some sense to x, because we have the functions that vanish on x should vanish there. And then in addition, we have this condition, which says that the last coordinate is 1 over f of the applied to the other coordinates. And that tells us how we should. So thus, Z is a closed sub, is first, so we want to show Z is a closed subvariety of an plus 1 isomorphic So that's what I want to show first. So we can define phi, which is supposed to define this isomorphism, but a priori we just take it as a map to an plus 1. Namely, if I call the coordinates on an x1 to xn, so this is 1 to n, and we take 1 over f, write 1 over f to say that's an element in ax. So 1 over this. So these are all regular functions, well, we see in a moment, from x to n plus 1. That means to point P, we associate its first coordinates until the nth coordinate, and the last coordinate is 1 over f applied to the first n coordinates. So as f has no 0 on xf, I wanted xf here, because we had precisely taken xf to be the complement of the zero set, we get this is a regular function on the whole of xf. So thus, phi is a morphism. Now, x, and we can easily see, you can directly check that our z here is the image. Now, X is a variety, so it's irreducible. XF is an open subset, so it's also irreducible. And we had an exercise, which I think was homework to give back today, that if you have a morphism, the image of an irreducible, or maybe if you have a continuous map, whatever, the image of an irreducible subset is an irreducible subset. So that means Z is irreducible. So as phi is continuous, Z is irreducible. Thus, an affine variety. And now phi is an isomorphism because I can write down its inverse. From X to Z, I mean, phi is a, as it goes to X goes to Z, it's a morphism from X to Z. Phi from X to Z is an isomorphism. Because we have the inverse is just the projection to the first n coordinates. No, I get back here. So here, this map is the identity on the first coordinates, and then it puts 1 over f. But just forget this. I get back to the original point. So it's just the map x1 to xn. Okay, so we see this. And as I said, corollary, at least if I use something I will show a little bit later, is that every point in any variety has a neighborhood which is an affine variety. Let X be a variety, quasi-affine or quasi-projective variety. Every point X has a neighborhood which is an affine variety. That means, practically that means if one wants to prove anything, if you want to prove something which depends, which is somehow a local property, so it's enough to know it for a neighborhood of every point, you can prove it for any variety if you're able to prove it for any affine variety. And if, assuming that the thing is invariant under isomorphism, then it means it's enough to prove it for a closed subvariety of AN. So if X lies in some, so our varieties are either quasi-affine or quasi-projective. So if it lies in projective space, so we have that our given and that P. So we take any point P in X, then will be contained in some of the open subsets UI. UI is where the ith homogeneous coordinate is non-zero. And we will see that UI is isomorphic n. So for the moment I use it. I have it here. So then we get the neighborhood of our point by replacing, so we can replace for our neighborhood UI, our point can replace x by x intersected UI, which is a neighborhood of P, which is isomorphic to a subvariety of n. If so, if here we have a closed the intersection of an open and a closed subset in UI, so on an isomorphism, it will be mapped to an intersection of an open and a closed subset in AN, which is a subvariety in AN. And so it's enough to deal with, thus we can assume X is contained in AN. Now it's not necessarily closed, so it's not by itself an affine irreducible closed subset, but we can write, but being a subvariety, it means it's an intersection of a closed subvariety with an open subset of AN. So thus X is equal to, say, X bar intersected some open subset V with X bar closed, so the closure in AN and V open in AN. Now, we know what the closed subsets in AN are, and therefore we know what the open subsets of AN is, so we can write V as AN minus the common zero sets of some polynomials. Where the GI are some polynomials in x1 to xn, because we know the closed subsets in AN are the zero sets of some polynomials. And so, well, as our point P lies in X, it doesn't lie in the zero set of the common zero set of all of them, so there must be one of them which is non-zero. X, I with I of P 0. So thus lies in bar intersected of X bar I, and is affine. Oh, obviously, the zero set of one polynomial is bigger than the common zero set of several. So this thing itself is an open subset of X, which contains P and is affine by what we just said. Okay. So this was just, this is somehow the abstract things. Oh, yeah, now we would like to do the same for morphisms to projective varieties. So a morphism to an affine variety was given by an n-tuple of regular functions. And we want to say that the morphism to the projective variety is also somehow given by something like regular functions or maybe rational functions. Again, it's a bit more complicated because you have these homogeneous coordinates. So it will be similar but not quite the same. And so what we still want to say that morphisms are given by tuples of rational functions. The morphism to a subvariety of Pn is given by an n+1 tuple of rational functions satisfying certain properties. Morphisms quasi-projective varieties. I want to be more sketchy because it's very similar to the affine case, but first at least a definition I have to get precisely and in detail. So let X be a variety. And so we first define an equivalence relation on tuples of rational functions. On, say, Kx n without the origin, so just, which is the usual equivalence relation, up to two things are equivalent is if they are these vectors are multiples of each other's. So by tuple f0 until fn of rational functions is equivalent to h times f0 until h times fn for any h rational function on X, not the zero function. And so so if you wish, if you divide by this equivalence relation, you somehow have the projective space over the field of rational functions. But maybe one doesn't want to talk like this. So we denote f0 to fn, the equivalence class. Okay, so it's an n tuple of rational functions up to multiplying everything by the same rational function. Proposition. So again, let X be a variety. And Y in Pn projective variety. The map X to Y morphism if there exists such an equivalence class of tuples of rational functions. So if and only if there exists an equivalence class 0 to fn of rational functions on the whole of x, or rational function on x, fi in kf, such that the following hold, such that we have two, such that for all x, we can find a representative of this equivalence class say G0 to Gn of this class, such that we have two properties. First, now these are rational functions. I require them to be defined at P. 0 to Gn are defined at P. And second, they are not all 0. So maybe and if I take the point, so and not all G I of P are equal to 0. I just say, and if I take G0 until n, this vector, this is not the 0 vector. And the second statement is obviously that this gives us this map. So phi of P is equal to the point in projective space, G0 of P until Gn. Okay, it's a bit more complicated than in the affine case, but the basic thing is just the morphism is given by an n+1 tuple of rational functions, where one can, however, choose up to multiplying all of them by the same function, and we have to find a representative so that we are able to put our point P into this tuple. So that means they are all defined. And we don't have that all of them give 0. So if we put them into the tuple and take the corresponding point in projective space, I mean, there is such a point in projective space. And then this point should be the image point. Okay, so this is, so, and then we write phi is given, is this map G0 until Gn. So it's a bit more complicated. As you see, we might have to, so now we don't have necessarily that these functions fi have to be regular everywhere. We just have to be able to always choose a different representative so that they are defined, but we have to hold the balance. One thing is to have them defined, and one thing is to have them vanish. If we kind of go too far and multiply it with something which vanishes too much, then they might all vanish at the same time, and then the map is also not defined. Okay, so this is this definition, this proposition. So we, now I don't, in some sense it is similar to the affine case, so I will be maybe a little bit sketchy. So one should maybe see, just to make sure, that if we do have this thing, at least this map is well defined. So it could be that we have several representatives. So we have, so we should have obviously that whenever this makes sense, we should get the same result. And so this is what is well, so this is well defined. So because we have So if we have another representative, then we could write this as h times g0 until h times c0 until h times gn. And if we put p into this and take the point in projective space, this is obviously, so this just means if we put p into it, we put also h of p here. Then this is, we are in projective space, so we have multiplied everything by the same. So this will be g0 of p until gn of p. So this definition is well defined. This gives me a well-defined map wherever these conditions are fulfilled. So now let me try to sketch the proof, but I don't want to go into too much detail. So again, it's an if and only if. So I maybe only talk mostly about one direction. So let's choose I such that y intersected with this open subset ui non-empty, and maybe our point. So then, and we call again the coordinate functions on y, we call y0 to yn, the homogeneous coordinates. So then we have then y0 divided by yi and so on. We have at some point yi divided by yi, which is just 1, and so on until yn divided by yi are rational functions x, and in fact they are defined on y intersected ui. And if we take any point in the inverse image of this, then we have, well, again, we coordinate-wise, we have this. So we have phi of p will just be y0 of phi of p until yn of phi of p. And if we are in this, so just as a point in projective space, and this is, I can also write this as y0 divided by yi of p until yn divided by yi of phi of p. We just have divided by this function yi, which is not 0 here. And so if we put say f I j to be phi star of yj divided by yi. So this is now, as this was a morphism, this is a regular function on U. So this is in O to the minus 1 of ui, particularly in the neighborhood of p. It's a regular function. And we have phi of p is equal to, this is y0 divided by I composed with phi. So this is just f f0I until fni. So this is just given by f0I until you're found in the neighborhood of this point. It's given by these rational functions, which are regular here in this open set. And you can check. So if the point also lies in another UI, you can find another such. So maybe I can write it here. Also lying in Y intersected UK, obviously can write in the same way. Get on -1 of UK, we get that phi is given by f0 k until fn k. Same. Of y divided by k, and you can check, and directly write down what is the function which you have to multiply all of these. So one function so that you get all those. Check that k nk actually equal, so this tuple is equivalent to f0 I n I. So that in fact the map is given by such a equivalence class of tuples. Okay, so this is essentially one direction. And so the converse is very similar to the case, to the affine case. You have to show that this map is both continuous and the pullback of a regular function on open subset is regular, and the proof is essentially the same as in the affine case. So we need to show that such a map phi equal to continuous. And satisfies that if I take phi star f is regular on phi to the -1 of u, f is regular on u, or u subset y. And this is the proof is the same as in the affine case. No, because one just uses again that continuous means that the inverse image of a closed subset is closed, and you can again see that the inverse, so the closed subset is therefore the zero sets of some polynomials, and if you compose it with this thing, it becomes a zero set of some regular functions, and also here with the pullback, it is the same. So let's Yeah, it's a slightly complicated definition, but on the other hand, one can get used to it. Sometimes it is useful to do things like that. You know, one really needs these rational functions here. One cannot talk, cannot just, you know, one can't just take functions which are regular on the whole of this projective, of this variety. In fact, one can find, later we will see, that the functions which are regular on the whole of a projective variety have to be constant. So then, if one would allow only functions which are regular everywhere and wouldn't do this thing that one can change this, one would, that one can take another representative, one would get that all morphisms from projective varieties to projective varieties would have to be constant. That means map everything to a point. That would obviously not be a very good theory. Okay, so let me see. What did I want to say? Yeah, I wanted to give a few simple examples and properties. So, for instance, if I take for instance, phi, to put it in this form, I can write it as 1 x1 divided by x0, 1 squared divided by x0 squared from p1 to p2. Morphism. So note that here, obviously, so these are all rational functions. Like this, it's only defined when x0 is non-zero. But we can also, after all, write the same in the same way. If I multiply by x0 squared divided by x1 squared, this is also x0 squared divided by x1 squared, x0 divided by x1, 1. And so these two open subsets, so the open subset where all of these are defined and non-zero, and all of these defined are non-zero, cover the whole of P1. And in both of these, it is defined in this way. So this is a morphism. The moment we see, you can also say it in a different way. So I want to have a few properties of morphisms which don't necessarily depend on this. You know, what is a morphism? So if X is a variety, U subset X open, then the inclusion U to X extends a point to itself, a morphism. Obviously, we would have expected that, but it's also with the definition. It's obviously, this is basically obvious because it's continuous, and you can easily see if you have a regular function on open subset here, the pullback will be a regular function on this open subset intersected with U, and so this is a morphism. So it also works for closed subvarieties. Let X be a variety, Y subset X be a closed subvariety. Then the inclusion of this closed subvariety is also morphism. Again, every point is sent to itself, is a morphism. Slightly less obvious. Obviously, it is continuous because Y carries the induced topology. No, the Zariski topology on the subvariety is always the induced topology. And with well, for the other statement, one has to have at least a little argument. So if U subset X is open and F is regular on U, so then obviously and say we take a point P, point in Y, then some neighborhood of our point P, we can write, so maybe I call this neighborhood V, we can write a regular function can always be written as a quotient of two polynomials in the ambient space. Either if one is in a fine space, then just two polynomials in the variables one has there, or if one is in projective space of two homogeneous polynomials of the same degree. But anyway, we can write f equal to g divided by h, where g and h are either polynomials variables if x lies in a n, or g and h are polynomials in n+1 variables, homogeneous of the same degree. That. And h does not vanish on V. No zero. So then, however, then on Y restricted, so Y intersected V, which is still a neighborhood of our point P, we have that, the pullback by the inclusion is just the restriction. So we have E star of F is just F restricted Y. Now, so on this thing, this can be written also just the same. F is just a restriction. So if this function was the quotient of these, then its restriction is the quotient of the same. No, it just says that for all P in V, f of P is g of P divided by h of P. So in particular, it's true on the smaller subsets. And so it is locally near our point P, the quotient of two polynomials, in the projective case homogeneous of the same degree, so it is a regular function. So thus, f is regular on okay, so this shows also the embedding of these are all kind of trivial things, but one wants to be sure that one can do the obvious things. Everybody think that if you just take the inclusion of an open or closed subset, that should be a morphism. But obviously the definitions have to give that, otherwise we have the wrong definitions. And so let from x to y be a morphism. So let say z subset x be a subvariety. Then if I take the morphism phi, I restrict it to z and view it as a map from z to y. This is also a morphism. It follows from what we have, because phi restricted to z is just the composition of the inclusion, so of phi composed with the inclusion I from z to x. So it's a composition of two morphisms, so it's a morphism. And we can also do the same thing on the target side. That's slightly less obvious. So let x to y be a morphism. Let z subset y be a subvariety. It can be either open or closed or locally closed. Then if I take phi and view it as a map from x to z, a subvariety obviously which such that phi maps into z. X is contained in z. If I then view phi as a map to z, it's a morphism. This is a little bit less obvious from the definition of morphism, because if it just says it's continuous and the inverse image of a regular map on an open subset is regular, it's not precisely clear how this should be, but it follows from our results here. We have that a morphism is something whose coordinates are given by regular and rational functions. So if we are in a fine space, it's given by an n-tuple of regular functions, and this doesn't matter on where we think we are going. We always are y lies in an and z lies in an, so that is fine. And if now y lies in Pn, it's given by this equivalence class of tuples of rational functions. Again, this it plays no role where we say the map is going. So this follows. By this definition, a morphism, if x lies in an, if y lies in an, a morphism from x to y is by this proposition that we have the same as a morphism from x to an whose image happens to lie in y. In the same way, a morphism phi from x to y, where y now lies in Pn, is the same as a morphism from x to Pn whose image happens to lie in y. Thus, this follows from description of morphisms. So in terms of rational, in terms of regular and rational functions. But in fact, this statement is actually, we really use this, and it is indeed true that if one generalizes further and would talk about schemes, such a statement would not be true. But we don't talk about such things. Okay. Now I had kind of promised you that I give. So one thing that we want. So we had identified an with an is bijective to this open subset ui of Pn, to any of these open subsets. And it had better also be isomorphic to it, and so we want to see that. So 6. So I from an n, or so to ui subset Pn was this map which sent a point a1 to an to 1 to so with the notation it doesn't work. Maybe I just say it for u0, it's the same for the others. U0 is equal to set of all points where the 0th coordinate is non-zero. So this is the set of 0. So then map sends this to the point 1, a1 to an, an isomorphism. So first it's a morphism because we can write it as, we can just write it as 0 is just 1 n. The xi are the coordinate functions on an, and it just does this. Here, actually, we are in a situation where all these are functions which are regular everywhere, and so this is. And the inverse map you also know what the inverse map is. This is just the map from 0 to, was I called this phi0 from n, sends a point n to 1 divided by b0 until the n divided by b0. So therefore, phi0, just if I call the coordinates on Pn, the homogeneous coordinates y0 to yn, this is just y0, y1 divided by y0 until yn divided by y0. So this is a quotient of two homogeneous polynomials of the same degree, obviously, and it doesn't, the denominator does not vanish on u0 by our assumption, and they are also not 0 all at the same time. So this is a morphism. So thus is also isomorphism, is also a morphism. So we have, and so an is isomorphic to u0, and obviously in the same way it's also isomorphic to any other ui by the corresponding map. So just as a mark, time is it's up. Oh, not so fast, but maybe I can. Yeah, a bit slower than I thought. So if we identify AN with U0 via U0, small U0, we get that every affine algebraic set X in AN is, it now means that, as this is an isomorphism, it means that AN carries the induced topology from Pn. So we know that the closed subsets of AN with this identification are the intersections of the closed subsets of Pn with U0. So affine algebraics can be written as AN intersected X bar with X bar subset Pn, the closure of X in Pn. Okay. So I think I will maybe today give you some exercise about this thing so that you have some concrete calculations that you can do. Just want to briefly talk about something simpler, which are also polynomial maps. So here I have said that morphisms to projective varieties are given by these tuples of rational functions, which is a bit unpleasant, but in some cases it's nicer. So these are further examples. Polynomial maps. So that X in N is a subvariety. So you can assume projective variety and assume F0 to Fm are homogeneous polynomials, are polynomials in X0 to Xn, homogeneous of the same degree. With no common zero on X. That means if I take the common zero set of all of them, intersected with X, this is empty. Then I can also define a morphism in terms of these polynomials. Then if I can denote it as F0 to Fm from X to Pm, which sends a point A0 to An to just evaluating all these polynomials at the coordinates of the point and taking the corresponding point in projective space. This is a morphism. One should maybe be slightly careful. Obviously, A0 to An is a point in projective space. Here we put in some representatives. So we choose A0 to An so that the class of it is this. And we have to choose the same representative of all of that, in all of them, and take the corresponding point in projective space. This is as usual. So this is a morphism. And such a morphism is called a polynomial map. And I mean, why is it a morphism? Because these have no common zeros on X, so we can cover X by open subsets where one of the Fi's is non-zero. So for E from 0 to M, we can write this map F0 to Fm is just equal to what we had defined before as F0 divided by Fi until Fm divided by Fi. So these all are, so these are now rational functions on X. And you can see that for different i's, they are equivalent. No, because we multiply by Fi divided by Fj. So this, and these have no, here we have so this thing, the denominator is non-zero on, so this is, I say, defined on this particular way of writing is defined on X without the zero set of Fi, because here then these are regular there, and they have also no, these F0 to Fm have no common zeros, as we had said. So this description of it, works on this open subset where Fi is non-zero. The union of these open subsets is the whole of X. So we have, again, according to our definition, this is a morphism. These are somehow the simplest morphisms because, that's what one would maybe like, that the morphism to projective space or to a variety in projective space is given by an n tuple of polynomials. But the warning is that not all morphisms say phi from X to Pn or for to any projective variety are polynomial. So that is, therefore we cannot just restrict our attention to that. Okay, maybe I will, I have some more examples, but I don't want to keep you longer. We can, let me see. No, there's a bit more. So we will, that's as much as I wanted to say about these morphisms, almost, except for a couple more examples. And then next, so I will finish that next time, and then I will talk about products and applications of products. Okay, so we'll see how that works. So we see each other next Monday then. And I will try either today or tomorrow to give you new homework, as you, in particular some concrete examples, because things were a little bit abstract now. Obviously, one always has to keep in mind what it concretely means, how one works concretely with it. Okay, are there any questions? Okay, so then.